Okay, so this is Experiment 8, pH titrations by Emily Steffen and Kelsey Jackson. Our purpose was to create pH graphs of titrations of strong and weak acids with strong bases to determine the Ka and pKa of those weak acids and the molecular weight of an unknown acid. For the experiment, we took 10 milliliters of hydrochloric acid was pipetted into a beaker with enough deionized water to cover the pH probe, so it covered the top of it so you could accurately measure the pH. And then a burette was prepared and filled with NaOH solution. So first we rinsed it with tap water, and then you would rinse it with deionized water, distilled water, and then rinse it with NaOH, so that was the only thing covered in the inside of the burette, so your solution wasn't contaminated. And then fill it to, in this case we filled it to 0 to start the titration. Then you added 1 milliliter increments of NaOH to the solution until there was a difference of 0.2, larger than 0.2 in the pH. Then once that was observed, you started adding the NaOH dropwise until this pH difference was large. Then you could go back to adding 1 milliliter increments, and that's kind of showed where your equivalence point was. Then they were added in 1 milliliter increments, like I said before, until the pH reached 12, and this was repeated for each titration. Part 2 was the weak unknown acid. We each obtained a weak unknown acid. Both of us had different unknowns. It was titrated with NaOH following the previous steps. For part 1, the strong acid and strong base, the concentration of hydrochloric acid to begin with was 0.1 molar, and the concentration of NaOH used, which was our strong base, was 0.103 molar, and the original pH of this solution before the titration began was 2.45. Then for the weak acid and strong base, the concentration of acetic acid, which was our weak acid, was 0.1 molar, and then our concentration of NaOH, which was our strong base, was again 0.130 molar. And the original pH of that solution was 3.61. For part 2, for the weak unknown acid and strong base, Emily's unknown, which was unknown number 28, the original mass was 0.2239 grams. And for the second unknown, which was unknown number 29, the original mass was 0.2201 grams. This is the titration curve of the strong acid and strong base, where we calculated the Ka and pKa. So you took the inflection point here, you drew a line from where it started down to the volume, and that was your equivalence point volume. Then you have that and drew another line to where it intersected with your titration curve, and then drew a line over to the pH, and that was represented your pKa. This is for the weak acid and strong base, and you did the same procedure to find the pKa again. And as you can tell here, previously the pH was very acidic for the strong acid, and here you can see the difference that it's a little bit less acidic due to the weak acid. Our calculations to determine the pKa of the acetic acid, you took the pKa which we found from the graph, and you took the negative log of that. Well, to find the Ka, you took the negative log of the Ka, so you would take 10 to the negative 4.5, which was the pKa found, to find the Ka, which was then found to be 2.5 times 10 to the negative fifth. The known value for acetic acid, the Ka, is 1.8 times 10 to the negative fifth. So then we found our percent error of that, and we got 39% error. For the unknown number 28, the titration curve is shown here, and we did the same thing to find the pKa. You just have it looked over at the pH. And then the same thing was done again. You had the pKa, so you set it equal to your negative log of Ka, took 10 to the negative 3.55, which was her pKa. The Ka was found to be 2.82 times 10 to the negative 4. Then we found then we started to find the molar mass of your unknown acid. So first you would find your moles of NaOH. So we used 13.4 milliliters of NaOH, so you converted that to liters. Multiplied that by the molarity of NaOH to get your moles of NaOH. And because there's a 1-to-1 ratio of your moles of NaOH to your moles of unknown acid, it was the same number of moles. Then you took the grams you had measured out for the unknown acid, divided that by the number of moles to get your molar mass. And we identified this as mandelic acid. For the second unknown, number 29, this is just the titration curve of that again. And then the same calculations, the pKa was found to be 5.2, and then the only difference is the different number of liters, which in this case was 10.5 milliliters, so you converted it to 0.0105 liters. And then you write your moles of NaOH, which equals your moles of acid, divided by, take the number of grams, divided that by the moles you found, which in this case was 0.2201. And then we identified this as potassium hydrogen phthalate.
Okay, and for our discussion, we had to write the complete overall and net ionic equations. So the first one is the overall equation for HCl and NaOH, and the second one is the complete ionic, and the third is the net ionic. And the same thing for the weak acid and strong base. And we noticed that the pKa and Ka wasn't determined for HCl, and this is because HCl is a strong acid, and it's 1 of 6, and we know that strong acids dissociate completely, so the Ka is completely irrelevant in the process. So then we had to compare the initial pH of the strong acid and the weak acid, and for our strong acid, it was slightly lower than the weak acid. I think the weak acid was around 3.6 and the strong acid was around like 2.5. And this is because a strong acid originally starts with a lower pH simply because it is more acidic. We had to compare the pH at the equivalence point for the strong acid and strong bases. And for the strong acid, it was around 6.7, and for the weak acid, it was around 7.9 for the pH. And these aren't the same, and this is because the strong acid is harder to overcome, so it takes more of the basic solution to get rid of it. After that, we had to compare the number of moles of the base required to neutralize the strong acid with the number of moles required to neutralize the weak acid. And when we did this, we noticed that more moles were required for hydrogen, or HCl, I'm sorry. And this is because the concentrations of NaOH are the same, so it depends on equivalence points. And it'll just take just as much NaOH to neutralize acetic acid as it will for HCl. For the titrations, we noticed that the pKa and the Kas were determined, and this was part of the purpose of our experiment. And the values were important to determine the molar masses of the unknown acids and to recognize which ones these were. And comparing with the chart, we noticed that they were very close. And these are our references.